Okay, let's go ahead and get started. So just normal updates here. So this week's lab is lab 8. Of course, I extended lab 7 till tonight in case you're still working on any of that. Lab 8, like I said, is a data collection lab. So it's really kind of meant to prepare you for the stuff that you're going to be doing next week as you start collecting data, input data on the sort of the systems that you're maybe thinking about picking for your final project. One thing about the input modeling report, which I'll mention in a second here, that we're not going to sort of check to see that your input modeling report definitely matches up to whatever you end up submitting for your final report. So if you end up finding out that actually this is not going to really work well, let's shift to this other system where it's much easier for us to find data on, that's fine. We just need to make sure that you are starting to practice the tools so that you are going to be well suited to be successful by the end of the semester with your final project. So it's kind of the goal with the input modeling report. So to prep for that input modeling report, we've got lab 8, where I give you a bunch of data sets that look like data sets like you might take out doing your final project. And then you'll end up doing some input modeling of those. And so you'll say, okay, this is a discrete random variable. This is a continuous random variable. We're going to fit it to this distribution. And you're going to learn how to use ARENA's input analyzer, which helps with that modeling stuff. So that's, and as we start using some of these tools, especially now that you're taking classes like 474, you might be familiar with other tools like JUMP or SPSS or whatever they're using currently in 474. And as we get closer and closer to your final project, if you find other ways to do these statistical tests that you feel more comfortable doing within those tools, I would encourage you to use those. But we are sort of just covering the kind of basics that Rockwell provides as part of the suite that goes along with ARENA, like the input analyzer. But there are plenty of other nice statistical tools that do the same things that are embedded within specific stats packages like JUMP or whatever you might be using in 474. So I know a lot of you taking 474, so feel free to kind of cross-pollinate, especially for your final project. As of course, for the lab 8, we really need you to use ARENA's input analyzer. You have to go through the process of using the Rockwell stuff at least once. But for the final project, you've got a little bit more freedom to do more sophisticated or stats and packages that you're more comfortable with. So that's what I was saying. Next week, there's no formal lab next week. It's just an open time for you to have time to work on your input modeling report. Then the 2 weeks after that are labs 9 and 10 as usual. And then after that, I think we've got 2 weeks left over in the semester. So those will also be open labs to help ensure that you can focus your effort on getting your final project done. So the final project, the description and all that is posted. I kind of gave the description of the basic outlines of this last time. It is a group project. I know sometimes there's friction in, oh man, he's making us work in groups, but it is one of the things that ABET, so the American Board of Engineering Accreditation, or the Accreditation Board for Engineering and Tech, I always forget what all the letters stand, but the accreditation board that that gives your degree weight so that you could potentially go off and take the PE degree sometime, then requires us to occasionally have classes that have you do group projects because you'll be doing group projects out in the real world. And this is just one of those classes that it's traditional for us to put one of those group projects. So I know sometimes it's frustrating. How do I find all this group and working with this group? And I feel like I could do all this on my own and everything, but it's really meant to be good practice for stuff that you'll end up having to deal with in the real world anyway. I've put an emphasis on having 4 team members. With the number of students we have enrolled in the course, there will definitely be a handful of 3-person groups. So if you're stuck at 3 and just can't find that 4th member, feel free to submit that name list. And if worst comes to worst, I can add people afterwards. So if it doesn't look like things are working out, but what may happen with the number of people in this class, if everybody did 4-person groups, I think we'll end up having like maybe 2 people left over. We might have 3 people left over, so then it'll all work out fine. But it's always awkward if we have just like 2 people left, because then I've got to maybe take 2 people off a 4-person group in order to make another group or something like that. So I'm not. if you really can't find a fourth and you really feel like you've got a strong three, you can feel free to submit that, and it may actually help the numbers work out. But you know, of course, we need a majority of 4-person groups, and that will end up giving you much better feedback when we end up doing the final project reports and presentations with the peer review, because you'll get more peer reviews, and it just generally makes it a little bit more manageable for us to have a smaller number of teams. So that's another reason why we restricted to 4. So the big deliverable that's due this week is the name of your team members. I think we've had about 5 teams so far that have submitted and are all set to go. So we're expecting, I don't know, anywhere between 12 and 16 teams maybe in this class. So the rest of you, just make sure that you submit this by this week. Every member of your team should submit this. It's an individual assignment, but that way I can confirm that everybody agrees who's in their team. And then I use this to create groups on Canvas so that the rest of the deliverables can then be submitted as group projects. So other assignments are out there. There's an ICA that is due before G3, ICA G3. This homework, I finally got updated. So that homework is on Canvas. If you'd like to start on this homework is 2 questions, as all these homeworks have been. The first question is basically doing a chi-square on a more general distribution. So something you might have seen in like 380 or something like that. And then the second question is a power analysis. And if you've never done a power analysis before, we'll go over that by lecture G3, but I also have some help that is posted right alongside this homework on Canvas if you want to get a head start on that. And then keep thinking about your final project. So again, big thing, form your teams, but then right after you form your team, start saying, what do you guys want to work on? And then say, well, you know what, this particular system on campus, near campus, in Tempe or whatever, you know, I think there could be an interesting thing that we could study there. It might be easy to get data, you know, and then, you know, start thinking about what you might want to put in that input modeling report, which sort of doubles as a proposal and kind of showing me that you've gone out and show me you have the ability to gather data from that system. So any questions about admin stuff going forward here? All right. Like I said, some of the lab, it looks like there's a little backlog from the availability extension with Shin. So I'm sort of working on trying to help them get through that so that you can get your lab 4 grades and move forward. Okay, so technically, so let me just make sure, any questions online? Looks like we're good so far. Okay, so where we were last time is we are now in this input modeling section. And so the idea here is that we view inputs to our simulation models. So our simulation models are these things that we draw. The inputs to these models are the random variables and processes that go into these, what like sort of the inside of these boxes here. So if you think about part 1 of lab 6, I had you basically have a create block and 2 process blocks and then a dispose. And I just had you then choose different distributions for interarrival times, or for processing times in those 2 blocks. And he showed that even though the means were the same in those, the distribution shape changed the output stats quite a bit. And so it goes to show that just because you've drawn the system the right way, then it still doesn't, that's not the whole story. And so the really important thing is making sure you get the random distributions, the variation that goes on inside these blocks. And that's kind of what we're doing now. And so some examples here is like for queuing models, you know, that we, you know, the interarrival times and service times are the things we got to make sure we model really correctly. So we go out in the real world, we measure real interarrival times, we fit them to say an exponential or whatever they might be. We measure real service times, we fit them to a distribution, whatever it might be. We put those distributions into Arena, and then we feel pretty comfortable that our queuing network is maybe is correct. And so all queuing networks might look very similar, but what really differentiates them is not the structure of the network, but it's the choice of these distributions. Same thing with the supply chain model. All supply chain models are going to have demand and lead times in them. What differentiates between one supply chain and is the demand distribution, the lead time distribution. Toilet paper became a very difficult thing to get, not because the supply chain changed the structure of it, but the demand distribution changed. The way people used toilet paper changed, and that is what affected the output stats. And so getting that demand distribution right is really important to getting the operations right. Reliability problems, the thing that we need to model are failure times. So from reliability problem to reliability problem, you'll always have a failure time you need to model. What differentiates between one and another are the different distributions of failure times. So the distributions of these are really important. Poor choices of these distributions give us poor outputs. So the easy part of this whole input modeling process is the hypothesis testing, as we'll learn in lecture G3. So in our next lecture, we'll learn the kind of very formulaic way, and you'll start practicing this on homework G3, where if you have a hypothetical distribution like this one, like this probability density, and I'm giving you a histogram of data like this one, then we can use things like chi-squared tests to say, is this hypothesis a good descriptor of these data? Or is it very likely that these data came from this hypothesis? That's the easy thing to do. The hard thing that we're trying to do now, that we're going to go into more in this lecture, is how do we build that hypothesis to begin with? So we've taken the data, how do we start with coming up with a distribution here, or even a family of distributions here? So that's kind of what we're doing. And so we talked about collecting the data last time. And so today we're going to talk about identifying that family of distributions that goes up into that corner. And then the next lecture, the last lecture in this sequence, we'll talk about parameterizing that distribution and evaluating our final best fit distribution to see what is the best fit distribution, but how good of a fit is it? And that's where we'll involve that chi-squared and Kolmogorov-Smirnov, again, in the more general setting, as opposed to just testing for uniformity like we did before the midterm. So that's kind of the roadmap of where we're going. So let's pick up with kind of where we left off last time. So if I think about, this is an example I said I'd make more concrete today. This is the security protocols going into a metal detector, say in a government building, or if you like an airport, if that's easier to picture. We've got entities, the people going through the metal detector. The metal detector itself is the resource that's constraining the people. Activity that we're worried about is the time to pass through the metal detector. And so in our first, just hearing about the system, what we do is we go into Arena and we grab the create block, and we grab a resource, and we create a resource. So we create an entity called people, maybe with picture person. We create a resource called metal detector, and with a fixed capacity of 1. So we create those, that's in the data module. So we're not dragging blocks into there, we're just in the little spreadsheet view. We go in and we create the entity and the resource type. And then we need to create the flowchart modules. And so we drag a create block in, and we say we're gonna have it create people. And so I'll show that in a second, drawn out here. And those people, we're gonna assume, arrive with a random exponential inter-arrival time in between them that we'll have to parameterize. And we'll then need to draw the process, which is the metal detector, which will seize, delay, release a metal detector. And the delay type is what we are now trying to model. So that's kind of the thing that we're trying to figure out, what's the right model for delay type here. And then we draw a dispose to collect the people. So I think I've got that here. This is our very simple metal detector system. You know, it looks like a single channel queue. And the key is, again, what we put in this middle one here. And so we've got all that here. And so we end up looking at our data, and we look at just the summary statistics for the process times of going through the metal detector. And it says the mean and the standard deviation are both equal to 30 seconds. So without actually looking at a histogram of our data, just looking at the mean and standard deviation, we might be tempted to just say, oh, it's got to be an exponential, because an exponential has got the same mean and standard deviation. So I'm going to go in and maybe I'll just put an exponential as my process distribution, my process time distribution, where I'm going to have the mean set equal to 30 seconds. And that will automatically make the standard deviation equal to 30 seconds for this. And so this is what that would look like. Now we can do that. That's easy to do in Arena, but we have to ask ourselves, does that make physical sense? And this distribution of metal detector passage times to me doesn't make a lot of physical sense. It doesn't take, I mean, it's true that there's a lot of density here at short passage times that you would expect in a metal detector, but there's also an appreciable amount of density here at like 2, 3, even like 3 minutes out here. So it doesn't take 2 to 3 minutes to walk through a metal detector, but here a significant number of passengers are, if we model the metal detector this way. So it just doesn't feel right here. So this is why, I mean, you always should look at the histogram of your data, but when you look at this, this should really tell you, before we move forward, let's just check to see, let's validate, is this a good model of the data we have? And so if we look at the histogram of our data, so these are real data, we see a bimodal distribution. And the bimodal distribution's got this sharp peak that ends at like 20 seconds, a gap where really nobody has these process times, and then another set of people that have process times between 60 and 80 seconds. So really, to me, looks like two populations. Now, when you see something like this, you can think, I don't know of any distribution in ARENA that's bimodal. So one of the things you could do is just use the cont, C-O-N-T, the cont function with your data set to create an empirical distribution. And we'll talk about that a little bit more in Lab 8. But when you look at this, that always should be a last resort. When you look at this, you'd say, is there something that I can change about the structure of my system that makes this easier to model using the building blocks, the fundamentals that I have in ARENA already? Yeah. Absolutely. Yeah, that is the way we would do. We sort of think of this as maybe this is a mixture of two processes, like you said there, where I've got a group here that is short passage times and a group here that's long passage times. And that is a way that instead of moving forwards, instead of saying, how am I going to shove this bimodal distribution through this block, we're saying, let's actually scrap this and let's redraw this with, as you say, two processes. And so that's what we'll move forward to do here, is that, so this is just showing, again, it's bimodal in the histogram. If I do a sample CDF, I get this flat plateau in the middle of the CDF. That corresponds to this gap here. And so whenever you see a sample CDF with these steps, that tells you that you've got two groups that are separated by each other. And so a way that I can deal with that is assume that these two groups are two different processes. And so I can cut everything 40 seconds under, and I'll say, I'm going to fit a distribution to that. And then I'm going to cut everything greater than that. And I just happen to plot it at 55, but you could imagine maybe I used 50 as my cutoff point. So everything less than 50, I'm going to fit something to. Everything more than 50, I'm going to fit something to. And now I've got two different types of processes here. And so now I just need to say, I need to adjust my system so that I can assign entities to go to one of those processes or the other. So that introduces a probability, a decision block in between. So I'm going to have a long passage time distribution. That's this one over here. I'm going to have a short passage time distribution. That's this one over here. And then I'm going to have this probability. And so I'll need to draw in, and I'll show you the flow chart here. I'm going to pull in a decide block and another process block. And just rather than having them use the same dispose block, I'm going to have another dispose block so I can kind of count how many I've disposed of out of one process and how many I've disposed out of the other. So what that ends up looking like is something that looks like this, where they all get created in the same spot. And then they go through this decide block here. And my hypothesis is that what's causing these two groups is that some get flagged as having something on their bodies. And so then they need additional checking. And then the rest of them just walk through quickly because they don't get flagged. And so I can have this detection block where most just don't trigger, and then so they go walk through and they are the quick entrance. But then the few that get flagged, they then get checked, and this check process, like, so this is the process of them actually maybe getting the wand or getting patted down, and then they get the delayed entrance. And so this maybe explains my bimodality here. And so what I'd like to do now is I take my, that normal is kind of that hump shape distribution. I'll put that in the get checked here. The exponential distribution for the short passage times, I'll put that in the walkthrough process here. And then I've got, the question of like, well, I might need to, figure out a probability to put here. Well, I can count how many, if I were to go back and look at these data here, I can count, Gesundheit, how many are in this group. And let's say there's 588 in this group. And I can count how many are in this group, 412. And then that tells me there's 1,000 total. And there's roughly a 58.8% chance that you get into the short one. So if I go to my detect block, I can put this as a 58.8% chance. And in theory, this is my new hypothesis for what's causing the data that I see here. So if I run this thing, I should get a distribution that looks like my real world data. And if it does, that helps me validate that this is a good model for the system. So I can run this thing, and I ran it with different detection probabilities. So here's a detection probability of 10%. So this is like people who really know that to take their stuff out of their pockets, and so they don't get flagged very often. So you can see that their mean, the mean of this whole distribution here is only like 11 seconds. And so it's mainly this peak here. With a 90% detection probability, you hardly get any of that low peak, and you get most of it up here. So their average time is about a minute. So you can imagine this is maybe an older population that isn't as familiar with this process. And so they're walking through with all of their belts and everything still on, and everybody's getting flagged. And so that's kind of over there. And then closer to the 58% that we see in our real data. And this does look a lot like the data set that I was given. So this is not the real world data set. This is a data set that Arena generated, but it looks very similar to the real world data set. And I can use actually tools like, which I haven't learned how to do this yet, but the Kolmogorov-Smirnov test, the chi-squared test, and actually compare this simulated data set to the real world data set and say, is it plausible that these two came from the same generator? And if I end up not detecting a difference, then I can say, wow, I've actually found statistically a good surrogate for the real world system. So I can start with this system, and then I can start playing with this system, and it'll be a proxy for playing with the real world. So it allows me to do my operations on this system here. All right, so questions about that, about these, how I got these data sets. Yeah.
So what happens if like the differentiation between populations aren't clear, and then like you can't like figure out where to provide it?
That's great. I mean, there's no, and that's the next example maybe starts to get into that. I mean, this is for one particular case where it's very clear distinction. But you're right, sometimes you're going to get these distributions and they're going to look weird, and there's not going to be a discrete break, and so eventually sometimes you do just have to go to the last resort and do an empirical distribution, which we'll talk about a little bit today, and also in the lab. So I can't say for like every single case this is exactly what you do here, but I'm just kind of showing you that part of the kind of problem solving that you will do as a simulation engineer is looking at these distributions and trying to come up with novel ways to explain the funny patterns that you get. And it's always better to explain the funny patterns structurally than just saying, that's just the pattern as it is. So you kind of want to say, like, you really want to make it so that whenever possible, you use the simple distributions we've been talking about, exponential, normal, or whatever. And then any variation from that, you can explain structurally by actually drawing, a different diagram, that when that diagram is instantiated with the simple things, they all mix together to create the complicated thing. You have much more confidence in my solution. Now that I've generated a bimodal distribution this way, I feel much better about it than I would if I would have just started with the bimodal distribution and shoehorned it into Arena and just said, Arena, draw things according to bimodal. I don't know why they're bimodal, but just go ahead and do it. So let's see sort of a different example here. And so this, it might have been when I looked at my data, I get something that looks like this thing, which has a bunch of spikes rather than two spikes. And so I have to feel like, and so if I look at the CDF, it has a bunch of stair steps. So remember, when you look at a CDF, the flat parts of every CDF correspond to kind of empty regions in the PDF. So one of the things you want to build up over time is the ability to just kind of like look at this and reconstruct this in your head and vice versa. And so the flat regions here are like the empty regions. And so I see a bunch of stair steps here or a bunch of chunky things here. And I think, well, what's going on there? Does my existing structure make sense of this? Well, my existing structure says I should pick off the smallest peak and put everything else in the slow peak. Well, if I do that, this is my fast peak that was far on the left, but everything else that's left over still looks pretty ugly. It's got a bunch of modes to it. All the modes seem to be separated by roughly the same difference. So any thoughts as to what structural process might cause this? Like, why would we get a bunch of modes declining in frequency, all separated by roughly the same time for like a metal detector? So before, think of it another way, in a previous example I did, then I had two groups. I had a group that went through very quickly, and another group that got tagged for extra screening, was manually checked and then allowed to go through. And so we had one group that was quick, another group that was slow, but they all ended up going through. So here, it's almost as if I've got a quick group, a slower group, an even slower group, an even slower group. It's almost like I have a bunch of groups that get slower and slower and slower, but eventually it's very rare for someone to be this slow. So what would generate these additional groups in a metal detector? If you think about what goes on in an airport, for example. What happens in an airport when, like if I walk through and I left my watch on, they'll probably tell me to take my watch off. And then what happens? I go back through, right? And so I go back through and then, oh, my keys. So then I take my keys out. And then what happens? Go back through, right? So there, at least in some of these security, eventually this might all stop and they'd say, sir, you've been flagged 3 times. We need to pull you aside and really see what's going on there. And so then they get the wand out, whatever. But it's simpler for them to, if you've identified what you think is causing the issue, to remove it and then send you back through. And so that could create these multimodal spikes. So if I look at each one of these spikes, so this is me looking at the spike from this first spike, and then I think I'm going to look at either this spike or the spike next to it. If I look at those 2 spikes in isolation, then what I find is the means are a little bit different, but the standard deviations are very similar. Now this spike has a lot less frequency. There's only 45 people in this spike, but there's 253 in this spike. And so there's a lot more uncertainty because I have less of a sample size here. But overall, it seems kind of plausible to me that these 2 might come from the same distribution. So what I might think here is this is actually the distribution I need for the time it takes to move through the metal detector. And I just need a process that causes some people to go through the metal detector more than once. So some people will go through once, some people will go through a second time, some people will go through a third time, and so on. Or rather, this is the maybe additional checking process before they send you back through the process. So I could build this instead. So what I've got here is now an arena model where I arrive, I go through the metal detector. This is my short time distribution, that kind of exponential looking thing. And then I've got a probability of, after I've gone through, what's my probability of being of triggering a detection here? If I don't trigger it, I get to enter, say, the airport. If I do trigger it, I go through an additional checking process where they say, is there anything on your body, et cetera, et cetera. You try to figure that stuff out. You end up putting it in the bin, and then you get sent right back through, and you walk through once again for additional screening. But then you might hopefully get through, but there's still a probability that you forgot something. And we maybe naively assume that the probability of detection is the same regardless of what pass you're going through. So that is something that we may need to improve. We may actually need to keep track of how many times. So you can imagine every time you go through this process, it actually increments some attribute. And then based on that attribute that got incremented, it changes the detection probability. Now, but we didn't do that. We're just keeping it simple. And so this will generate multiple, some individuals that just can cycle through over and over and over here, but eventually they'll all leak out through this absorbing state out here, and eventually everyone will get out. So this little structure here has the ability to generate these data. In fact, these spikes, I actually use that arena model to generate these spikes. So that's the reason why I don't have another data set, because this data set was actually generated in arena to begin with. So I'm not saying this is all of the cases you're going to see, but what I'm just trying to motivate is I want you to be looking at these histograms of your data sets, because the shapes tell a story. So you start out with your mental model of what you think the system, how you think it works. And that's a good place to start. And that tells you what data to collect. And so from that mental model, it said, I need to collect data on the inter-arrival times and the passage times through the metal detector. Well, then once you collect that data, it's a scientific process. So you might have to revise your hypothesis. So based on what you get here, you might say this data set would be extremely unlikely to be generated by the simple structure that I drew. So based on this funny data set, I'd say, what other structures could I add that give me this pattern for free, so that I can go from a complicated distribution like this to simple distributions like this one. And then once I've come down to a simple distribution like this one and the right structures, then I have a much more realistic system. So it allows me to trickle in the realism up to a point where I can say that is enough. So I might have needed to add a flexible detection probability. That might be the next modification I need. But eventually, all models are wrong, but some are useful. This might capture all the salient features that I need, where the big thing here is that individuals stay in the system much longer than I originally thought they would, because they're cycling. And it might suggest operational things, like maybe I need to make sure that these people get priority so that they don't get queued up again. So maybe the queue that's associated with this process, this resource here, maybe that queue isn't just a simple FIFO queue. Maybe it's a priority queue where it prioritizes people based on how many times they've been through this. That might be an operational change that I want to add there, and so on. So that's kind of my story about how you try to use your mental model and your data to go back and forth and revise these things. Other questions or comments about this process, either from in class or online? Yeah.
Would it be possible to have like a second metal detector?
Sure. So you mean like a metal detector just for this group here?
Like for the metal detector, would that be like different arrivals, or
Well, you could do another decide to go to another metal detector, but the simplest way to implement that would be to go into the resource in this walkthrough process and change the capacity from 1 to 2. And by doing that, then if anyone comes up to the metal detector, they'll go to whichever one is idle, if one is idle. Yeah. But if you wanted to say, well, this is not just any metal detector, this is a special metal detector that only people with the priority access, like only the TSA pre-check or something like that get, then you would definitely need a decide block, and you'd have to say, are you TSA pre-check or not? And if you're pre-check, you go to the special metal detector that maybe doesn't have some of this other stuff because they've already been kind of pre-checked, and so they can get through quicker. Any other questions about this general model building structure? Looking online as well. All right, so that's kind of where we were last time, is that how we look at our data, collect the data, and we use it to inform these structures. So now we're pretty confident that we like the structures that we've picked. And so we need now to figure out what distributions to put in them. So, and let's just do, for kicks, let's do an attendance exercise now. I haven't done one mid-class for a little while. So, question I'll ask here is, are there any, oh, I don't want to, there's actually, that's a sort of a trick question, so I'm not going to do that. So the question I'll ask here is, I think I already asked this one before, but I'll say, what is a continuous distribution whose mean is always the same as its standard deviation? I think I might have asked that last time, but it was easy come into play or come into mind there. Okay. All right, so yeah, so now we're confident about our structures. We now need to just move through and put the right distributions in those boxes, in those process boxes, in those create boxes. And so how do we do that? So that's what we're kind of going to be talking about here today. This is sort of the big process we've gone through the collect data, and now we're kind of in this gap here. So we are going to focus on, okay, we got our data. So not only do we, summary statistics are always very tempting, just take means and standard deviations or whatever, but the histogram, that's what we definitely need to look at the shape of the data. So we're talking about how do we histogram, then physical intuition by the process. Once we got the histogram, there might be some ambiguity in which distributions we're going to pick. And so we need to use our physical intuition to try to say, all right, maybe it's that distribution over that distribution because this system has this physical property versus this other one. And then once we've kind of got all of that, then we need to say how good was our guess. And so we're going to be talking about PP plots and QQ plots, which you probably have seen before in some of your other classes. The so-called fat pencil test, applies to these things. And so helps us give a qualitative assessment of whether we've made a good choice here. So then next time, then we will then talk about how we then choose, a quantitative choice of parameter, and how do we then do a quantitative assessment of our final choice here, how good of a fit that distribution is. So it's a little more qualitative all today. All right, so histograms. So you've all generated histograms now for homeworks in this class, probably in other classes as well. So they can be really useful in just figuring out the rough shape of a distribution. So for continuous data, you can kind of view them as an empirical PDF. So they look a little bit like the PDF. For discrete data, you can view them as kind of an empirical PMF. And so they're an approximation of the mass function. So, but the big trick in these histograms is figuring out how many intervals to choose and how wide those intervals are. And so this depends on a lot of things, how many observations and how variable the data are. A good starting point, so the heuristic you should maybe use is for continuous data, the number of bins, equally spaced bins, is the square root of the sample size. And so if I have 100 samples, and I'm pretty sure it's continuous data, I choose 10 bins and each bin has the same width. So that's the kind of general rule that you start with. You don't necessarily end there, but that's a good starting point. If it's discrete data, it's always scary to bin discrete data because you might bin outcomes together. And so with discrete data, the general rule is to bin each outcome separately. And so even though there's not a lot of outcomes, so like for a Poisson, if you think it's a Poisson random variable, or if it's just count data, for example, you might have data for 0, 1, 2, 3, all the way up to 10, but 0, 1, and 2 don't really have a whole lot of data points, and neither do 3, 4, and 5 or whatever. And you might be tempted to group them together and say, well, 0 through 2, I'll put in one bin, 3 through 5, I'll put another bin or whatever. But that can end up, that's great for continuous, but it can end up kind of really messing up the shape of the discrete. So with the discrete, even if there's a very low number of outcomes, we usually bin each outcome separately. So we'll see examples of that. So For continuous data, like this one here, this is all the same data, but just different choices of bin numbers. And so this, I would say up here, is too many bins. It looks too noisy. This almost looks like the real data. Most of the bins only have one in them. It's okay for some of your bins to have one in it. But when most of your bins only have one in it, then it gives you the impression that there's like a huge chunk of uniformity. It like kind of looks like it's like a uniform distribution, a uniform distribution, a uniform distribution. Like I don't get a lot of information out of it. I would argue that this one here is too few bins or too wide bins, because here I've lost all of the real variance in the data. Now it really does look even more like it's just a uniform distribution, a uniform distribution, a uniform distribution. There are too many underlying hypothetical distributions that would fit that. So it doesn't allow me to discriminate. It's kind of like at the other extreme, I can imagine one bin would go all the way across at a single level here, and it would just wash out any choice that I would want to make. I couldn't tell the difference between it and anything else. So down here, I would say this is probably a good choice here, because I've got a significant number of counts in every bin, and it shows me that I've got some useful shape here. Like it kind of gives me the impression that the mean of this is probably around here. It's also kind of symmetric. The mode is roughly there as well. It falls off roughly the same on both sides here. So I start getting a lot of good feeling that I can kind of guess at a smaller number of plausible distributions that fit here. So these two don't help me pick. This one is, it's almost too much like the data. This is almost too stylized. This one's right in between. So unfortunately, there's no, it's more of an art than a science here as to what the right choice is. But I just hope you can see that this looks like it's too fine. This looks like it's too coarse. And this looks like it's somehow close to being just right. I can't tell you for sure that this is just right because of X. Like I can't give you that objective rule, but I hope you can kind of get the feeling here that this is better than these two. All right, any questions about that? So when you're histogramming, don't take Excel's word for it. If you end up getting something that looks like one of these two, then go into that histogram properties and change the number of bins and see if the shape changes a whole lot. So that's kind of what I do, is like I'll change, like if I make my bins go way too high, things will start looking like this. If I make my bins go way too low, it'll start looking like this. And there'll be a range of sizes in between the number of bins where things don't change much and they all kind of look roughly like this. And when I get kind of that convergence of the middle, that in between there, where I could choose 50 bins, I could choose 49 bins, I could choose 52 bins, and I still get roughly the same shape, and it's illustrative of some interesting properties, then I think I probably got things about right. Okay. Question online. Oh, that was my attendance question. Okay. All right, discrete. So I mentioned with the discrete one, so this is data I've taken from a discrete distribution here. So these are arrivals per period, so they're count data. So 0 arrivals. So how often do we get? So imagine we've got, we're looking at an airport, and we're looking at arrivals per hour. And so we're saying, how many hours did I have 0 arrivals? And they were saying there were 12-hour intervals where there were 0 arrivals. That's the way you would read this. And so there was 1 hour interval that had 11 arrivals. So I looked through all this, and I've got arrivals per period, and I wrote out all of them. And even if there was maybe one that had a 0 frequency here, I probably would still write it out because I want to kind of include like all the possible counts here. And then I histogram that. Now in this case, if these were continuous data, I might try to maybe recluster these. But in this case, because they're discrete data, because I know that the outputs here are counts, they're these whole numbers here, then I don't want to join these things together, because it's going to make it harder for me to figure out what the appropriate discrete PMF is that I'm trying to match to this. So then I histogram this, and notice there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That corresponds to each one of these. So the 11 frequency rows here, I've got 11 bars here, no rebinning. So 11 bins correspond in the same, 11 outcomes, 11 bins. And so when I look at this now, I try to think of all the discrete probability distributions, which probability distribution could have a shape that looks like this. So does anybody have a guess? A discrete probability distribution that has a interior mode, so it doesn't start at the mode, it can go up to this mode here, that looks like potentially could go off to infinity. So are there any discrete probability distributions you can think of that could go to infinity that also can have kind of an interior mode as opposed to just being constantly decreasing? Any guesses? So a triangular I would call is a continuous distribution, which would be bounded, where triangular I would say would have a hard min and a hard max and a mode in between, and the triangular usually would represent all continuous values. So on the discrete side of things, can we think of a discrete distribution that has no max, even though, I mean, these days, all data are going to have a max, you have to take a finite amount of data. But this looks like it goes off into infinity. So what's a discrete distribution that's supported from 0 to infinity? And then unlike an exponential, which isn't discrete anyway, or I'd say, like, for example, this is not a geometric. A geometric distribution would be continuously decreasing. It would be highest at 0, and then it would go on down. So what is another discrete distribution that might have an interior mode, a middle mode? Yeah. I'm sorry, was that a hand, or is that just a Poisson? Oh yeah, right, thank you. Yes, both. You're both correct. Poisson, that's the one I would choose here. So when you see distributions that are discrete count distributions that tend to have these interior modes, a Poisson is usually a flexible distribution you should try. That should be in the families you should think of. It's not necessarily the only one that's a possibility. If we think more about it on the kind of non-exponential side of things, like there's like a negative binomial, there's or a binomial distribution, you can get these interior modes as well. But the Poisson, a Poisson is very often going to be shaped this way, with a lot of mass, and then goes up in mass and then falls off quite a bit. So so yeah, that's the Poisson there. So that's just kind of that's an extra exercise here. So which families do we like to pick from? If you're working with ARENA, it's nice to pick from the families that ARENA already has. Otherwise, you got to do that inverse transform mess that we did pre-midterm. It's good to know that the inverse transform method exists. I have to use it still myself, but if you can get away with not using it, it's great to not have to. And so it's great to try to find families that ARENA or whatever your simulation tool can already do for you without doing the inverse transform. And the way you find those is if you build any expression inside ARENA, you can right click on it, go to the expression builder, it'll pop up this thing. And under expression type, one of the categories is random distributions. And so these under random distributions here, they're not necessarily grouped by continuous or discrete. So you kind of got to know, you got to recognize it here, but they've got a long list of them there. And so those are the ones that are kind of like your first contenders. All right, so we've so we've looked at the histogram, and so the shape of the histogram is super important, but then also the context and physical properties are really important. So is the variable, does it go to infinity or not? Well, there are some distributions, like a binomial distribution doesn't go to infinity. So a binomial distribution, you say for 20 coin flips, how many flips come up heads? Well, that's bounded at 20, so it can't go to infinity. If you've got something that potentially looks like it could go to infinity, then you got to choose the distributions that can go to infinity. Is it discrete or continuous? That's like super important, discrete or continuous. And then other features that you can kind of tell here. So we'll kind of walk through some of that here in a second. Now, you're never going to get the perfect distribution. So remember, all models are wrong, but some are useful. And stochastic modeling necessarily leaves details out. So we're generating variation with randomness so that we don't have to generate variation by coming up with mathematical rules that respond to every tiny little variable that we might have to simulate in our simulated world. So we're going to leave something out. So we're just getting a good approximation for a complicated process. And so we've got these frequent ones, which we've been talking about here. And so I've given you a list in lecture D2, and then like I said, ARENA has also got its own list. All right, so discrete or continuous. This is something that you'll also get in the lab. This is the first thing, whenever you look at your data set, this is the first thing you should ask. Am I looking at a discrete random variable or a continuous random variable? If you look at your histogram and it's got giant gaps in between outcomes, it might be discrete. It might be you've binned over a bunch of continuous outcomes in a multimodal distribution, like we started the class with today. But if you look at these and you zoom in and all of these outcomes are identical, and all of these outcomes are identical, and all these outcomes are identical, then it's discrete. If you look at the histogram and it fills the whole space smoothly, then it's continuous. So just kind of drilling down into this. So if I take this histogram and I instead plot its sample CDF. So remember, I'm just going to take all the outcomes and I'm going to sort them, and then I'm going to plot them by their normalized order in that ranking. So outcome 2 is the first order I get, and there's roughly, so this is 10,000 samples, and so roughly 20% of the samples were outcome 2. And so, that's goes up to around 20% before we move on to the next outcome, outcome 3. So that's where this 20% comes from here. So all I'm doing is I've taken all my data points and I've sorted them from lowest to highest. And then for every data point, I've then plotted them against their ranking in the list. And so outcome 2 very quickly climbs to 20%. And then we're over at outcome 3, which climbs 70%. Then we're at outcome, whatever this outcome is here, between 5 and 6, it climbs 90% and so on. So these stair steps in the sample CDF tell me it's probably discrete. So I just get these vertical rises with these flat plateaus, and that is a telltale sign of a discrete random variable from data. If I instead plot all my data points against their rank in the sorted order, and they rise smoothly, where there's no repeated data points here. So they just kind of, they just keep rising and then eventually level off here. That's the telltale signs of a continuous. And so continuous data, sample CDFs are smooth, discrete sample CDFs are choppy. And so that, now usually with your discrete, once you've sorted them, you'll be able to see, do I get a lot of repeated values? And a lot of repeated values is the other sign of discreteness. All right, so questions about this, about how you visually tell the difference between discrete data and continuous data from the kind of the histogram side of things and from a sample CDF side of things. You'll get more of this in lab 8 as well. That makes sense? Questions online? Okay. I love sample CDFs because you don't have to worry about binning. So you just sort and plot, and there's no binning decisions you have to choose. So if you get used to using sample CDFs, it can greatly simplify the process. And then so once you look at those shapes, then you go back into your mental database of the discrete and continuous distributions that you remember, and you try to match them and say, does this look like one of these? Which one of these could this possibly be? If really it doesn't look like any, then, and you'll talk about this more in lab 8, you can, from the discrete side, you can load your data into the disk function. And so you can just say, I'm going to generate a distribution which is just going to use the data as a model. And it's not going to be one of any of these. It's just the ARENA will generate something whose stats match my data exactly. Similarly with continuous, you look down through the continuous distributions, If none of them quite match, then the cont function inside Arena, you can load your data up into, the sample CDF into, and it will then generate data that has a consistent statistical properties as your data. It will generate samples in your simulation that statistically match your data, but you just won't have any insight into what underlying distribution is there. So as a last resort, you can use disk and cont in Arena, and we'll talk about that more in Lab 8. So, so the next couple of slides, we're just gonna just remind us of some of these common ones. So a normal distribution, if you see symmetric, so interesting features of the normal distribution, if you see symmetric characteristics of your histogram, that sort of says, maybe this is a normal distribution. A normal distribution is kind of the telltale symmetric distribution. There are other symmetric distributions, but it's one of the ones you should think of. Is there some reason you might believe that your distribution could be supported from negative infinity to infinity? Is there some reason that you might if you were given just the mean, like I said, if you're given just the mean or the standard deviation and not given the histogram, then a normal is a great one to pick. Is there a reason why you might expect these data to come from an additive process? So if you're talking about how long does it take to make a sub sandwich or something like that, well, that has a bunch of parts that each one of their own random variable. And if you don't need to model each individual part, you just model the whole sandwich making time, maybe that's a normal distribution. So it would make sense that maybe that's up here. So things that are additive tend to be these normal distributions. Another common one you're going to look at is exponential. So you look at your continuous data point, and if the histogram kind of has this decline here, or the sample CDF has this nice rise, whereas no inflection point, then it might be an exponential. So exponentials have this memoryless property to them. So if you're like, if the data you've got are like waiting for a bus data, well, you know that waiting for a bus doesn't have that memorylessness, because you know that the longer you wait for a bus, you actually have a good idea that the bus is probably going to come sooner and sooner and sooner. So if you're in a process that doesn't have the memorylessness, then maybe you shouldn't choose the exponential. Constant failure rate. Is there any reason for you to believe that you're in a reliability problem? If you are modeling the reliability of a light bulb or something like that, and you know physically that these things tend to fail, none of them live longer than 10 years. And so as they get closer to 10 years, then they are and they'll fail any day now. These any day now type of failure processes probably aren't good exponential processes. And so these are things you kind of look at, is that, can I really model this as an exponential? And then if you say, based on this failure time distribution, that I can't model as an exponential, but it looks like it has features of an exponential, then you start modifying it. You say, what if it's a Weibull? So the Weibull distribution is used by by reliability engineers to model failures, which have this property where they will never fail outside of 1.5 years. They'll always fail before 1.5 years, and there'll be a big hump of failures right at 1 year. And so the Weibull ends up having some of the curviness that looks like an exponential, but it's been modified by this shape parameter that allows it to be bent either down towards the axis or up into these humpy distributions. So it's like if it looks kind of exponential-like in the tail, but maybe it doesn't look like an exponential near near zero, then maybe a Weibull is what you can use to kind of shove it into place. And so it's kind of what I'm just saying here. So the Weibull engineer or reliability engineers using what's called a Weibull plot to help evaluate the Weibull fit. So if you take a reliability course, then you might use Weibull plots that help you sort of try to guess what these shape parameters are. So this shape parameter that I'm calling K here, so you can kind of say for these data, what is the right K that I want to pick? And then you can plug that in there, and Arena supports that. And then we already talked about the Poisson distribution. It's really great for count data. So number of events occurring in a fixed time interval. So how many arrivals do they get in an hour? Often going to be a Poisson. And if I get very large Poisson parameters, because a count of arrivals is additive. You're counting it. A Poisson will necessarily start looking like a normal. So Poissons get symmetric as that parameter gets very, very large. And so even, so that's the nice thing about Poissons, is they can look kind of geometric, sort of exponential, but they can also get a little humpy, kind of like the Weibel, or they can get symmetric like a normal. So Poissons have a lot of flexibility as well on the discrete side. All right. So questions about any of those descriptions. So those are kind of like the key ones you should start looking for: exponential, Weibel, normal, and Poisson. The first three for continuous, the last one for discrete. Any of those sort of descriptions confuse anything? All right, so now we're talking about Poisson. So this next couple of slides here, when you're looking at your data, or you're going to start taking data for your final project, a lot of you are going to have to deal with interarrival times. And the hard way to deal with interarrival times, or sometimes it's just necessary, is to sit there with a stopwatch and wait for every single person to come into your system and measure the time in between them. That's one way you can get an interarrival time distribution. But there is a relationship between the Poisson and the exponential that makes collecting exponential data easier if you first think about the Poisson counts. So if you're pretty confident that you have exponential interarrival times, rather than modeling the interarrival time directly, model the count of individuals in an interval and then back out what the corresponding exponential rate will be. So what do I mean by that? So if I look at a Poisson distribution like this, so remember that the parameter of a Poisson distribution is the mean of the Poisson distribution. So if I look at this thing, remember the mean of a Poisson distribution. I heard people talk about statics earlier and said statics is such a worthless class. Well, to me, in retrospect, statics I thought was one of the most important classes I took as a young engineer. But at the time, as an electrical engineer, it maybe didn't seem that relevant. But but statics tells me how the center of mass of this distribution is probably roughly around here or so. So this is where it would sit at static equilibrium if there was a fulcrum right here. And so I can kind of guess this is roughly where the mean would be, but I could also calculate the mean using moments. So I can calculate the moment of this thing. And if I could figure out the mean of this distribution, that's the one parameter you have to worry about with Poisson. And once you know that parameter and the interval of time, you can back out an exponential rate that corresponds to that. So here's my example for this. So let's say I go to an airport, and rather than counting the interarrival times between every single person who arrives at the airport, instead, I say I'm going to model the 9 to 10 a.m. hour for every weekday. So I then break that 9 to 10 a.m. hour up into 10-minute blocks. And I say, how many people arrive in this 10 minutes, and the next 10 minutes, and the next 10 minutes, and so on. And what I'll end up getting is a distribution of how many people arrived in those 10-minute blocks, maybe across all the weekdays, Monday 9 a.m., Tuesday 9 a.m., or whatever. I just pull them all together, assuming that weekday 9 a.m. is the same, regardless of if it's Monday or Friday. And I get a distribution that looks like this, which means the average here is that 50 people arrive in every 10-minute block, sometimes as few as 30, sometimes as much as 70. Well, this here, I can fit to a Poisson. I can say, this looks like a Poisson. It's nice and symmetric because this alpha value is very high. And I can say my best fit Poisson here has an alpha value, a mean value of 49.9. So that's saying that the estimated parameter for the Poisson is that there is an average number of 49.9 arrivals per 10 minutes. Well, what I can then do is say, well, I'm just going to divide 49.9 arrivals per 10 minutes, and that will tell me how many arrivals I get per unit time, per minute. And that will give me 4.99, so roughly 5 arrivals per minute. So I just divide the alpha by the interval, so 49.9 divided by 10, and that gives me my lambda, which is my rate parameter for the corresponding exponential. So then I go over here and I say, all right, so if I want that, and it looks like what I've done here to make things more exciting is I put things in terms of seconds. So I took that 49.99 and instead of dividing it by minutes, I divided it by 10 minutes times 60 seconds or 600 seconds. And that gave me 0.08 arrivals per second. So my lambda predicted from the Poisson is 0.08 arrivals per second. So this is a real histogram of the data that correspond if I were to go out and take inter-arrival times from these data. So I said the easiest thing to do is just to count how many people arrive every 10 minutes, and you get this. Well, if you happen to also count all of the inter-arrival times, you would get this histogram. And the dashed red line that's on top of that, that is the exponential distribution using the rate I got from the Poisson estimation. So by counting arrivals per 10 minutes, I was able to then estimate this inter-arrival distribution parameter without ever actually having to take the inter-arrivals themselves. So that's a much easier to do. So that's kind of a trick there, is that there's that relationship between the Poisson and the exponential. If you're confident that you have over an interval, like an hour, it's the same exponential rate, rather than taking every single inter-arrival time, just count in sub-intervals of that interval, like 10 minutes out of an hour, and then fit a Poisson. And once you get the best fitting Poisson parameter, divide by the interval length and do whatever the unit conversions you need, and you'll get your exponential. Yeah.
So is there a difference
Yeah, well, absolutely. So like you in your sim, you need to simulate the inter-arrival times. So it may not be just possible for you to simply say how many arrived in this 10 minutes. So my sim is at the resolution of seconds. And so that's why I needed the inter-arrival time data. But I can take the data much more coarsely. So I've taken 10-minute coarseness data to simulate seconds of fineness inter-arrival times. I could have started with the inter-arrival times as fine, but it's just a lot easier to do counts than to do the stopwatch here, especially when you're talking about an airport when people are just flying through. Any questions about that? That's a real common trick to go from Poisson to exponential and back. Really simplifies your data collection. All right, so all I've got here, I'm not going to go over all of this, but if you're looking for a primer on, I've got this distribution, how do I implement it in Arena? I've tried to give those kind of in purple here whenever that's relatively simple to do. So these are, so some of them are easy like plus, but like a discrete uniform has a little more sophisticated formula, and it's got, again, kind of a little summary of why you might use that. Same thing with continuous. If you're looking for the syntax in Arena for a given continuous, I've kind of summarized them here, as long with why you might use that. And then again, I think I do that again here with more continuous. And then if worse comes to worse, as a last resort, you can take your sample CDF, raw sample CDF, and then dump it into disk if it's discrete, or cont if it's continuous. And Arena will generate data that will statistically match, even though you may be missing out on those important structures like we talked about when we started the class. Only other warning I'll say here is as you start working with the input analyzer, which you'll learn about in Lab 8, it will want to fit the gamma distribution to everything. It's such a flexible distribution. The gamma distribution is the Erlang distribution, where K is allowed to be any integer, or sorry, it's actually any real number. And so it's extremely flexible, but very often it's not really much better than an Erlang or an exponential or a Weibel. And so if you choose a gamma as an input model, be ready to defend that choice. Because if I'm scrutinizing, I might say, well, why did you choose a gamma? It seems physically like your system is more like an Erlang 5. It's got a sum of 5 exponentials. And if you just say, well, Arena said gamma was a better fit, then I'll say, well, how much better of a fit? If I guess is the R² value gives you is pretty darn close to a Weibel or an exponential. And whenever possible, it's better to choose distributions with fewer parameters. So if it's got the same R squared or roughly the same R squared, but fewer parameters, then it is a much better fit. And so if you take later classes in statistics, you'll learn about what's called model selection. And there's actually a metric called AIC, which balances the R squared value against the number of parameters. And you compare models based on their AIC, which is, again, that metric, which says if they've got fewer parameters, they're a better fit, even if maybe the R squared value is a little lower. So you have to consider both of those simultaneously. I want you to, at least now, we don't know about AIC now, but I want you at least in your head to feel a pull towards distributions with fewer parameters that have roughly the same fit. All right, questions about that? You'll get more of a feel for that when you do the input analyzer stuff inside Lab 8. You'll see that it's very, it favors the gamma distribution, the Erlang distribution very much. And that's pretty much just because they have an extra parameter. And so they can overfit data a little bit more. So I would rather you have a much more generalizable fit that has fewer parameters, even if it's the R squared value isn't quite as high. And that's all I'm kind of saying there. All right, so the last, we might have to wrap this up a little bit next time since we only have a couple of minutes here. But just to give you kind of an idea of where we're going with this, once you've picked that distribution, then, and again, I'll go over all this next time, but we're going to be doing these QQ plots and these PP plots, which are a qualitative way for you to plot your data against your hypothesis and to see visually if those things line up or if they're a bad match for each other. And so those of you who've taken a classes where you've talked about the fat pencil test, they're just using QQ plots and PP plots. And so we'll talk about both of those plots. You do the QQ first and then you do the PP, and we'll talk about that again next time. And there's all sorts of patterns for that. And so once you've got all of these QQ plots and PP plots, then we will be able to move on to what we will talk about next time, where we'll be able to actually then come up with a way to choose the best parameter and then evaluate using chi-squared and KS tests, like you're going to do on your homework with the chi-squared here, about now that I've picked what I think is the best distribution, let me actually then put a number on how good it is. And you might find out that it's so bad that you really do have to go back to the drawing board. But the hope is that it ends up not being rejected and you've chosen a test that has so-called high statistical power, so you can feel pretty confident in your model. So that's where we're going from here. But that's all I've got for you for today. So let me close with the attendance question, and we will pick up with PP plots and QQ plots next time. And that question is, and I'll put the URL back in the chat. And the question I've got here, let's say, if the best fit Poisson parameter is 45 encounters per 10 minutes, then what is the best exponential parameter per minute in per minute units? So 45 encounters per 10 minutes, and I would like to generate an exponential for the interarrival times, and I want that to be in per minute units. So the Poisson is 45 every 10 minutes, and I want to know what would I get in per minute units for an exponential. And that's all I've got for you. So I will hang around here for a little bit if anybody has any questions. Otherwise, I will see you on Thursday. And if there's any questions online, I'm happy to take them. Otherwise, that's all I got for you guys too. And so you can feel free to head out.